Hello, calculus students, and welcome back. Today we get into Chapter 10, which is the big chapter in BC Calculus. And we begin with learning about what power series are. First of all, let's remember some of the interesting results that we have about infinite series. You remember that we looked at a series like this, and this is an infinite geometric series in which the first term is 1 and the common ratio is a half. We have a formula for that. It's 1 over 1 minus a half, and this comes out to equal 2. Always a surprising result. Another very important series that we will look at is called the harmonic series. There's only one, and it looks like this. And the question is, does it converge or diverge? And that's a big question that we'll ask of many of these infinite series. In other words, this series up here converges to 2. Does the harmonic series converge, or does it diverge? In other words, does it just get bigger and bigger and bigger? And how about this series? 1 minus 1 plus 1 minus 1 plus 1 minus 1, and so on. Does it converge or diverge? One of the things you might be tempted to do is say, okay, well, this chunk is 0, this chunk is 0, this chunk is 0, so the whole thing is 0. And we'll see soon that that might not be the best way to look at it. So in Chapter 10, one of the things that we'll be doing is finding the techniques that will enable us to answer the questions converge, diverge, among others. So I suppose it makes sense to make sure we understand what an infinite series is, and it's simply of the form a sub 1 plus a sub 2 plus dot 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 plus a sub n, and continues and continues. And it can be written using sigma notation like that. And one of the things we say is that each of these are called the terms, and a sub n is the nth term. So we need to have language down before we can go on and talk about this stuff. So again, let's talk about some language. So suppose we have an infinite series, a1 plus a2 plus a3, da 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 da. What we do then is talk about a sequence of partial sums, and we have to really concentrate on making sure that when we say series, we mean series, and when we say sequence, we mean sequence. So this sequence of partial sums will denote like this. The first partial sum is just a sub 1. The second in this sequence of partial sums is a1 plus a2. The nth term in the sequence of partial sums is a 1 plus a 2, and we add them up until we get to a sub n. And so now what we have here is a sequence, an infinite sequence, sort of representing an infinite series. And essentially what we say is this: if the limit as n approaches infinity of s sub n converges to L, then so does the infinite series. So what we're doing here is we're relating an infinite sequence with an infinite series. And one of the ways that we can try to decide whether an infinite series converges is by looking at the sequence of partial sums and asking whether it converges. Now, if this doesn't converge, if this diverges, well then so does the infinite series. So let's think again about this kind of interesting infinite series. That, before we said, well, that's 0, and that's 0, and that's 0, so probably the whole thing is 0. But let's analyze it more closely with a sequence of partial sums. So the first partial sum is 1. The second partial sum is 0. The third partial sum is 1. The fourth partial sum is 0, and so on. And once we understand that that's our sequence of partial sums, it is pretty clear to us that the limit does not exist. And so therefore, this infinite series does not exist, does not converge. And that's one of the powers of this idea of the sequence of partial sums. So I said this limit doesn't exist. We could also say that the limit diverges. A limit either converges or diverges. Okay, one more thing to consider. Suppose we have, let me make that infinity. Suppose we have an infinite series which converges. Then one of the things that we can say that must be true is that the limit as k approaches infinity of a sub k must equal 0. And we'll see about this later on, that the converse is not true. In other words, we can have an infinite series in which the terms are approaching 0, but such that the infinite series does not converge. More on that in a later section. So let's remember about an infinite geometric series, and this is what an infinite geometric series looks like. Now, if this converges, then we know that, number one, r has to be between -1 and 1, and we also know that the limit to which it converges is a sub 1 over 1 minus r. We say then that the interval of convergence is r between -1 and 1. So that's a new term that we want to become familiar with. Interval of convergence. Those are the values of r for which the infinite series will converge. Okay, so let's take a look at these two examples. In the first one, we see that we have an infinite geometric series in which a sub 1 is 1 and r is -1/2. So this will converge, and it converges to 1 over 1 minus r, which turns out to equal 2/3. If we look at the next one, we have to be careful here, because what we notice is that, our first term is pi over 2, big deal. But in this case, r is equal to pi over 2, which is greater than 1, and so this diverges. Okay? Okay, so now let's get into the real work. Let's begin by thinking about 1 over 1 minus x. And if we actually do this division, what we'll notice, and you can do this out, is we get 1 plus x squared, and so on. Never ends. If we also think about this series, 1 plus x squared, and so on, we can recognize this as an infinite geometric series where the first term is 1 and r is x, and as long as x, absolute value of x, is less than 1, this is going to equal 1 over 1 minus x. So that's sort of two ways of thinking about this. But in either way, what we get is the fact that this function, this very, very simple rational function, can be written like this. Now, you'd want to say that this is a polynomial, but it really isn't, because it never ends, and a polynomial must have a degree. And so this is what we see is our first example of what we will call a power series. This is a series. It's a series that involves variable x, and it's actually equal to a function 1 over 1 minus x. And it's important to always remember that this equality only holds when the absolute value of x is less than 1. Okay? Okay, so here's the big definition. This infinite series is called a power series centered at x equals 0. And this is a little bit more general. This is a power series centered at x equals a, and we call a the center. And so one of the big questions we'll ask in coming days is, what are the values of x for which this infinite series converges? And indeed, what function does it converge to? So a lot of interesting theory coming, but for right now we just want to make sure that we get the definition of exactly what we mean by a power series. So one of the things we want to see here is that we can create new power series from existing power series. Here's the first one that we have looked at. Now, if we can call that f of x and just replace x with minus x, we have a new function g, which is alternating. And then if we take g and replace x with x squared, we come down to this series. And so you'll begin to see how important it is to be able to build up new series from existing series. Now check this out. If we have a power series, and it's the function it represents like this, one of the things we can do is differentiate both sides with respect to x, and if we do that, what we're going to get is 1 over 1 minus x quantity squared is equal to 1 plus 2x plus 3x squared plus dot 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 plus n times x to the n minus 1 plus dot dot dot. So what we have here is a brand new power series and the function that it represents. And I suppose it's important always, although we generally don't do this, to continue to say that this equality only holds when the absolute value of x is less than 1. So similarly, we can integrate. So let's look at the second one of these functions that we had when we replaced x with minus x. And now what we'll do is we'll integrate from 0 to x on both sides, and we're replacing x with t just as a dummy variable. And when we do that, we get the ln of 1 plus t from 0 to x is equal to the integral of this side is t minus t squared over 2 plus t cubed over 3, and so on. And we integrate that from 0 to x. And if we do that, what we have is the ln of 1 plus x, a brand new function here, is equal to x minus x squared over 2 plus x cubed over 3 minus x to the 4th over 4, and so on. A brand new function, and we obtained it by integrating. So now what we have is a power series that represents the ln of 1 plus x. Pretty cool. So it probably is a good idea to make this statement as we move along, that if we have some power series, and we're able to show, and we will find out how to do this later on, we're able to show that it converges for all x in that interval, well then so will any series that we obtain by differentiating f of x or by integrating f of x. Now it may be that the series that we get when we differentiate converges for a larger interval, and the same thing with the series that we get when we integrate, but at least we can be sure that those new series that we get will converge at least in the same interval that the original series converged in. Alright, so let's look at our first very cool result. So remember we showed that 1 over 1 plus x squared is equal to that power series. Now, if we integrate, and just as we did before, what we're going to get is this. The arctan of x, the integral of 1 over 1 plus x squared is arctan of x, is equal to x minus x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7, and so on, an infinite series. And now we're going to let x equal 1. And we will be able to show later on that when x is 1, this series does indeed converge. Well, if we let x equal 1, what we get is the arctan of 1, that should mean something to you, is 1 minus a third plus 1/5 minus a 7th, and so on. And what does the arctan of 1 equal? What's the angle whose tan is 1? Well, that's pi over 4. And so what we've just shown here is that pi over 4 is 1 minus a third plus a 5th minus 1/7, and so on. So this is an infinite series, and not only does it converge, but we see that it converges to pi over 4. How wicked cool is that? Alright, so here's our final mind-blowing example. So let's suppose that we have some infinite series, a power series, defined as follows. Remember, you've seen 2 factorial means 1 times 2, 3 factorial means 1 times 2 times 3. And what we're going to do is differentiate it. So the derivative of this function, well, is going to equal 1 plus, now when you take the derivative of this, do you see that you get x? And when you take the derivative of this, do you see that you get x squared over 2 factorial? And similarly, the next one is going to be x cubed over 3 factorial. Oh my goodness gracious, that tells us that f prime of x is exactly equal to f of x. And we can also go back to the original function and recognize that f of 0 is equal to 1. So if we let y equal f of x, what we have is an IVP, in which dy dx is equal to y, and y of 0 is equal to 1. Now we have learned how to solve these IVPs, which separate 1 over y dy is equal to dx. We integrate both sides, and if you do that, it won't be very hard for you to show that this function y, f of x, is exactly equal to e to the x. So where did that come from? Pretty amazing. So this function right up here is exactly equal to e to the x. So you're going to hopefully think about that and say, well, how can I start with a function like e to the x and get the power series? How can I start with a function like sine of x and figure out what its power series is? Or the function ln of x? All those good questions will be answered in the next section or two. So I promise you that this is going to be a very, very important and very interesting chapter, and hopefully you believe it. See you next time.